Hi everyone. It's my great pleasure to introduce my mentee, İbrahim Emir Çiçekli, who is an undergrad student at Galatasaray University. First of all, I am very thankful to him for being such a hardworking and dedicated student. During this summer, he has read about a master thesis called Application of CM Elliptic Curves, which contains basics of algebraic number theory, the theory of elliptic curves in general, and the reduction of elliptic curves and CM method, and finally Schoof's algorithm for point counting. Given the time constraint, he will be only talking about Schoof's algorithm, but he did a great job. Thanks to him again. And floor is yours, Ibrahim.
Well, first of all, I would like to thank my mentor Eda for her kind words and continuous support. And I would also like to thank the DRP organizing committee for this opportunity. As my mentor said, I'll talk about Schoof's algorithm, which is an algorithm for counting FQ rational points on an elliptic curve for a given finite field FQ. But before I get into my outline, I would like to give my opinion on why you might be hearing about elliptic curves like for the 50th time in this talk. There are, I think, two principal reasons, one of which is that elliptic curves are mathematically interesting objects, in my opinion. They are the simplest case of an abelian variety of dimension 1. An abelian variety is an algebraic variety with a group structure on it. They are very prominently used in number theory, one of which you might know is its application in the famous proof of Fermat's last theorem by Andrew Wiles. But also, I think one of the main reasons why it's been getting more popular since the late 80s and 90s is their practical uses. They are used in elliptic curve cryptography, which I will explain now, and they are used in integer factorization, which is factoring integers as composites of smaller integers. Elliptic curve and other methods are used in it as well. While to explain the elliptic curve cryptography part, so in public key cryptography, we have a public key and private key, and we have a cryptography problem that uses those two keys. And a cryptography problem is usually given by something called a trapdoor function. A trapdoor function uses those keys to generate another value. But the point of a trapdoor function is that a trapdoor function easily takes the value A and computes the value f of A, but it is very hard to invert. It is very hard to go from f of A to A. And that is the basis of public key cryptography. Elliptic curve discrete logarithm problem and isogeny-based cryptography uses these simple methods. I might get into this later if time permits, but for reference, let's say I have a elliptic curve cryptography problem that uses a public key of size 256 bits to get the same amount of security from a RSA cryptography, which uses prime numbers and their decompositions. I would need to have a public key of size 3072. So key sizes are much smaller, which makes it for smaller key sizes, I get a higher amount of security, which makes them very useful. This is my outline. I will again define elliptic curves and give their properties, basic properties. I will talk about isogenies and endomorphism ring of an elliptic curve. I'll introduce the counting finite field points of an elliptic curve. I will give you the naive approach to solving this problem, which was used before Schoof's algorithm. Then I'll give a brief summary of Schoof's algorithm. So what's the elliptic curve? That's an elliptic curve is a curve, non-singular projective algebraic curve of genus 1 over some field K, which has a group structure. They are usually given by a Weierstrass equation. And if the characteristic of our base field is neither 2 nor 3, we can simplify Weierstrass equation to this form using some very simple change of variable, which will luckily be the case through this talk. We'll never deal with characteristic 203 case. It's a very difficult computation. Here I put some examples of elliptic curves over R. We can see their graph. So what's the group law? We take 2 points on the curve. We draw the line passing through those points, and that line will most of the time intersect the curve on a third point, which we'll call for now R prime, and then you can think of it like taking the reflection by x-axis or just drawing a line from the point at infinity, and then that intersects the curve at another point, at a fourth point called R, and then I define the composition of P and Q to be that fourth point. There are two questions to be asked. What happens if I want to compose a point by itself? I consider the tangent line passing by that point. And what happens if it doesn't intersect in the affine drawing? And then in this case, we see why it is more natural to consider an elliptic curve as a projective curve, because then we are guaranteed that it will intersect at a third point. In this case, we say it intersects as a point at infinity, which will function as the identity element of our group. I went into effort of explicitly writing the group operation, but we won't need that. Now we can state that with this operation and this identity element, elliptic curve, the points on elliptic curve form an abelian group. And also another remark is that just as we said in yesterday's talk, if we take rational points on the curve and we adjoin the point at infinity, it forms a subgroup of our original group E. Again, very important, two special quantities that are attached to an elliptic curve with this Weierstrass equation form. They are called the discriminant and J invariant, and they are defined as so. You can verify that the non-singularity of the elliptic curve is given by the fact that whether the discriminant vanishes or not. And J invariant is called so, it's an invariant, because it turns out that isomorphic elliptic curves have the same J invariant. Isomorphism in this context means rational maps between elliptic curves. I would like to give some extra remarks, but the converse is not necessarily true. If two elliptic curves have the same J invariant, they need not be isomorphic over the base field that we have chosen. I have given a quick example here. We have two elliptic curves. If you consider them over the base field Q, they are not isomorphic over Q, even though they have the same J invariant. Because in order to write a map from one curve or to other, I would like have to write a map like this, and square root of 2 is not in Q. Therefore, this is not a map over Q. It's a map over either we could consider Q adjoint square root of 2 or algebraic closure of Q. So they are isomorphic. If they have the same J invariant, they are isomorphic over the algebraic closure of the base field. Here's a E1 and 2, E2 drawn on graph. This is why considering elliptic curves with isomorphisms is not very interesting, because we already know the explicit formulas of isomorphisms, and if they have the same J invariant, they are isomorphic over its algebraic closure. It's not very interesting. That's why we consider isogeny maps. Two elliptic curves, E1 and E2. A morphism of curves is called an isogeny if it takes the point at infinity of one to the other. In other words, if it's a group homomorphism. Here I gave a very important example that will come up later. It's called a multiplication by M map. We take a point and compose it with M times. Since this is a group law and E has a group structure, you can verify that this is a well-defined map. We have another important subgroup of our elliptic curve, which is called an Antergen subgroup. For a given positive integer n, it's the set of subgroup of points that, when composed n times by itself, that vanish. It's called an Antergen subgroup of E. Now, what's an endomorphism ring of an elliptic curve? That is, for a given elliptic curve E, the set of isogenies from E to itself. With pointwise addition and map composition, this set has a ring structure. And as we have seen, each integer gives a isogeny. So we can embed the integers into the endomorphism ring of an elliptic curve with this map. And most of the time, that is the whole story. The endomorphism ring is equal to Z. But in the special case where the endomorphism ring is bigger than Z, we say E has complex multiplication. And I would like to give where does that name come from. It comes from a very specific example. If you define an elliptic curve over C like so, and if you consider this map turns out to be an isogeny. And as you can see, if you plug in the equation, it gives another same equation. And this is why it's called complex multiplication. And it turns out the endomorphism ring of this particular elliptic curve is the Gaussian integers. Here's another example for over a finite field with characteristic bigger than 3. There is always complex multiplication since we have a map where we raise each coordinate to the qt power thanks to the Frobenius endomorphism. This is not an integer multiplication, but it's an isogeny. So this special isogeny is called the qt power Frobenius endomorphism. It will come up later in Schoof's algorithm. And this implies that if our elliptic curve is over some finite field, there is always complex multiplication. So what is our problem here? For reasons, practical reasons is cryptography, in order to know how hard our cryptography problem is, it is very useful to be able to count finite field points of an elliptic curve. That's why we want to know how many points, because then we can determine how hard our cryptography question is. The naive approach is the most straightforward approach that anyone could come up with. For a given x coordinate in our finite field Fp, for a p prime bigger than 3, we have two possible cases. Either this expression x cubed plus ax plus b is not a square in Fp, the field Fp. In that case, we don't have any solution of the form xy. If it's a square in Fp, if it's 0, we have one solution of the form xy. If it's non-zero, we get two solutions of the form xy. And then if we count our over the points in Fp, if you count this expression where the expression with parentheses is a Legendre symbol, this means that if we count over that expression, we count the Fp points of the elliptic curve. Why is this called the naive approach? Because it's not as fast as we would like it to be. Calculating Legendre symbol takes polynomial time, a polynomial in logarithm of p, but since we calculate p Legendre symbols, it comes up to p times log p. But an efficient algorithm should be a polynomial of log p, not p. And Schoof's algorithm does precisely that, but we need to get over two very quick theorems. One is called Hess's theorem or Hess's upper bound. It gives an upper bound to the number of Fp points. The proof is a little bit tricky, so we won't get into that. It states that this expression is smaller than 2 times square root of q. The negative of this expression is called the trace of the Frobenius endomorphism. The name trace comes from some linear representation of the endomorphism ring. We don't need to get into that. And another theorem is that this Frobenius map satisfies this characteristic polynomial. I don't know about you, but when I see this expression and when I know that this A stands for trace, the Cayley-Hamilton theorem comes to my mind. So I can see that this is also related to the linear representation of the endomorphism ring. So what does Schoof algorithm do? It aims to benefit from the upper bound from Hess's theorem, the Frobenius isogeny, and something called division polynomial. Division polynomials are defined as so. They encode the torsion data. That is to say, if a point xy on the elliptic curve, for example, satisfies the polynomial psi2, that means that's a 2 torsion point. If it satisfies psi3, that means it's a 3 torsion point. We keep track of torsion data with these polynomials. To give a quick overview of the algorithm, we have the setup as before. And by Hess's theorem, we know that the number of FT points is equal to Q plus 1 minus T for some T in this range. Now, to compute T, it is sufficient to compute T modulo N for some N bigger than this value. We choose this a little bit bigger than this upper bound to avoid some technical difficulties that would take a lot of time to explain. To compute T modulo N, now for a given random integer N, it is not easy to compute T modulo N on computer. So we do the prime factorization of N by primes Li, and then we compute T modulo Li for primes, and computing the modulo value for primes is much easier. What does that give us? If we compute T modulo Li for each Li, then we can use the Chinese remainder theorem to lift that value, T modulo N. So, since the Q power isogeny satisfies this characteristic polynomial, for a given prime L, if I were to plug a L torsion point on this equation, we will get something like this. As you can see, these are all polynomials of the x and y, coordinate-wise. But I can reduce this problem even further. Since I have chosen an L torsion point, there is some unique integer T bar less than L such that T bar is equal to T modulo L. Now, since our point P has order L, not necessarily order L, but its order divides L, T times P is now equal to T times bar P, T bar times P. Now, we reduce the coefficients of the original equation by modulo L to get this one. Now we have to basically check for which T bar less than L minus 1 and greater than 0, this equation is satisfied in order to get the value of Frobenius trace modulo L. And then we lift for each L using Chinese remainder theorem and get trace modulo N. What does torsion polynomials do? They, as I said, keep track of the torsion data. And how do we use them? Now we have the polynomial ring with 2 variables x, y over the field fq. And when we divide that by the equation of elliptic curve and N torsion, the division polynomials, we get a ring in which we have significantly reduced the degrees of our polynomials, which improves the computation time. And also each Rn keeps track of the N torsion data via division polynomial. If time permits, we can get into the discussion of runtime complexity. How much time do I have? 2 minutes, okay. I don't want to explain this step by step. This is basically a pseudocode of our algorithm, which also exists in my project report. You can check it if you want there, or we can talk about it in tea time. I would like to give some closing remarks about the improvements on this. In 90s, Elkies and Atkin improved Schoof's algorithm. This is the core of the algorithm that is used today, but they have somewhat improved the algorithm. Remember, we originally had a set of primes Li that are prime factors of our N. They reduce those set of primes to a special set of primes called Atkin primes and Elkies primes. And prime number L is Elkies if this characteristic polynomial splits over FL. If it's not Elkies, it's called Atkin prime. And they somewhat managed to show that they can use the information from Atkin and Elkies primes to produce a better algorithm, which is the algorithm that is used today called Schoof Elkies Atkin algorithm, CEA for short. And the problem is now, in this case, is to determine how to efficiently determine if a prime is Elkies of Atkin. And they use something called modular polynomials to determine if it's an Elkies of Atkin prime. Modular polynomials are a study of subject in a field called modular forms. And modular polynomials basically give something called modular curve, which is closely related to elliptic curves. And if I run out of time, that's pretty much that. Do I have 1 or 2 minutes? If it's okay, I would like to explain what elliptic curve discrete logarithm problem is. Now, like I said, we need to come up with a trapdoor function. And as you have seen, we have a group law on the elliptic curve. What can a cryptography problem that we can come up with is the problem like this. Suppose that I have some non-zero point P on elliptic curve, and I consider the subgroup generated by that point, so that we have a group with a single generator. Then I can take a random point, let's say Q, that is inside this subgroup. Then this means that for some integer m times P is equal to Q. Now, as a trapdoor function, it is relatively easy to compose P by itself. It can be shown that this multiplication by integer map can be expressed with division polynomials as well. So they are useful in that computation sense. It is easy to compute Q from P and M, but it's not very easy to return from P and Q to the exponent of this element. So this is a cryptography problem in a sense. Isogeny-based cryptography is a little bit more complicated. We can't get into that. And thank you for listening.